Hello everyone, welcome to the first hands-on session. Today, we're going to work on a 2D truss structure example using finite element method. First, I'm going to introduce you to some terminology regarding FEM. Then, we're going to learn how to assign boundary conditions for the truss structure that we're going to work on. And finally, we're going to work on the element stiffness and global stiffness. So to start off, this is the example we're going to work on. As you can see, we have 3 nodes, which are represented by yellow markers. We also have the elements, which are represented by gray lines. So this is a structure that we're going to work on. We have the material properties for these elements. These are going to be used in the stiffness calculation process, so keep that in mind. Now, first, let's start with the terminology. I will use these short forms for these terms in my code, so don't forget about these. We have number of nodes. We have nodes per element, number of elements, problem dimension, and finally we have the extended node list, which will be in the size of number of nodes times 6 times problem dimension. So let's start by defining the coordinates of the nodes in this structure. I'm going to store the relevant information in a matrix called node list, which will be represented by NL in my code. So the size of this matrix will be number of nodes times problem dimension, because for every single node, I will have X and Y coordinates. So that's why we have the size of number of nodes times problem dimension. So for the first node, the coordinates are 0 to 0, as you can see. For the second node, we have X is 1 and Y is 0. And for the third node, we have 0.5 as the X coordinate and 1 as the Y coordinate. So if we go back to the code, let's start by importing NumPy as NP. All right. Let's define, by the way, I created 2 Py files. One will be for the whole application and one will be for the functions. So I'm writing this to the fem.py. I suggest you to do the same. All right, so let's create the matrix. This will be 0 to 0. I also have to put this in another bracket. All right. In the next line, the coordinate is 1 to 0. And finally, we'll have 0.5 to 1. 0.5 to 1. So these are my coordinates. Next up, I also need to store the element list, which will be represented by EL in my code. The size of this matrix will be number of elements times nodes per element, because for every single element, I will have 2 endpoints. So for example, for the first element, one endpoint is 1 and the other one is 2. So this is the first element, this is the first node, and this is the second node. So I will put this in my matrix for the first element. For the second element, it's going to be 2 and 3. And for the last one, it's going to be 1 and 3. So let's write that. I'm going to define another matrix. And then I also need to put these in the bracket too, comma, this is gonna be 2 to 3, and finally this is gonna be 3 to 1. The order of the elements doesn't matter, so keep that in mind, because this will be fixed in the code later on by degree of freedoms and DOCs as well, DOCs. So don't forget about that. Now, we have the node list and the element list. And by the way, let me just clear this. Okay, and then clear this as well. All right, now we have the node list and the element list. So let's assign the boundary conditions to the structure. Let's fix the node 1 in both directions, x and y. And let's also fix node 2 in y direction, but it'll be free to move in the x direction. And finally, I will let node 3 move freely along both axes. But I will apply a force 20 newtons downwards to the node number 3. So I'm going to create another matrix to represent the boundary conditions that I assigned. So let's say, so the first node is fixed in both directions, which means it's going to be a Dirichlet node for both directions. As you've seen in the class, we represent those with -1. For the second node, it's free to move in the x direction, but it's fixed in the y direction. So we're going to have 1 for Neumann and -1 for Dirichlet. And finally, we have the third node free to move in both directions. So it's going to be Neumann for x and y. And don't forget about the comma. All right. So we have the boundary conditions. If you notice, we also have a force, so we have to represent that in another matrix. So let's say FU is MP dot array. So for node 1, we don't have forces, external forces. So let's just do this. Oh, by the way, let's talk about this before moving on to that. So far we have the node list, which will be the first 2 columns of the extended node list. We have Dirichlet and Neumann, which will be the 3rd and 4th columns of the extended node list. We have the DOF and DOCs here, but we shouldn't calculate these by hand. The program will calculate these automatically. For Dirichlet nodes, it's always going to be 0 because they cannot move in those directions. For the rest of them, we don't know them, but initially we're going to assign 0 for all of them. So this is why I have question marks in here, but I'm going to assign 0 to them in my code. For Dirichlet nodes, the forces are unknown, so the program will calculate it depending on the stiffness and the functions that we're going to assign. The rest will be 0 and the force that we assigned, which is -20 in the negative y direction. So let's represent the force in an array. So for the first node, I'm going to start it by 0, the question marks, because we don't know them. For the second one, it's 0, 0 again. And finally, for the third one, it's 0 to -20. 0 to -20. So that's it. I also need to represent the displacements. So it's all going to be 0 because these will be 0 and will not change. And these will be initially 0, but the code will change them by itself. So let's just copy this and then change the values with 0 for all of them. So we have all we need to start. We have the example written in these lines. All right. So let's define the Young's modulus as 10 to the 6. And let's define the cross-sectional area as 0.01. Because this is what's given in the question. Now, I'm also going to define the problem dimension, which will be np.size nl node list in the column in the second direction, which will be the number of columns. So 1 and 2. The problem dimension is 2. I'm also going to define the number of nodes, which will be np.size nl0. The number of rows will represent the number of nodes in nl. So that's it. I'm also going to start the extended node list with full of zeros. So let's say np.zeros. The size of this array will be, as we've discussed here, number of nodes times 6 times problem dimension. So number of nodes 6 times problem dimension. Once we've done that, we can start assigning the node list to the NL. So to do this, I'm going to change ENL's first 2 columns, all of the rows and first 2 columns, which will be from 0 to problem dimension. So it's going to be 0 and 1. These 2 will be equal to NL itself. I'm also going to assign the boundary conditions that we've written here. So that will be the, let's say, from PD to 2 times PD, which will give me 2 and 3. So this will be equal to D or N, the whole matrix. Let's run this. So what's... Oh, okay, we just missed a comma here, so nothing important here. So if you run this, now we can see that the ENL has the node list in the first 2 columns, and on the third and fourth column we have the boundary conditions. The rest will be 0 for now, but we're going to fill them with the functions in a few moments. So let's come to the first function that we are going to write. I would like my function to return a tuple of ENL, DOFs, and DOCs. And the name of this function will be assign BCs, which will take the parameters as NL and ENL. So I'm going to pass the node list and ENL to this function, and then in return, I'm going to update the ENL, and I'm going to get DOFs and DOCs. So let's define this function in here. Define assign BCs. The parameters will be NL and ENL. All right. So let's start with defining the number of nodes, which will be as in here. I'm just going to copy these two and then paste it because it's going to be the same thing. I also need to import numpy here as well. Import numpy as np. All right. So we found these. I'm going to assign DOFs is equal to 0 and DOCs is equal to 0 initially. And then we're going to update these two in the upcoming for loops. So let's start with the loop for I in range 0 to number of nodes. For every single node, I'm going to look at the problem dimension. So for each node, I'm going to go through the columns x, y, x, y, x, y, and so on. So if this one is a Dirichlet node, which is the case for the first node, let's represent it by if ENL, the node number, which will be the first node initially, and then problem dimension plus j. If this is Dirichlet, so let's see. It's going to be the first node. It's either going to be 2 or 3, which will go through these two columns. So if it's -1, I would like to do, I would like to subtract DOCs minus equal to 1. So I'm going to subtract 1 from DOCs. And then I'm also going to update, so 2 times PD plus J is equal to DOCs. I'm also going to update this portion here with -1, -2, because it's Dirichlet. If it's Dirichlet, you just subtract 1. If it's Neumann, you add 1 to DOFs. So that's what I'm doing here. On the other hand, let's just keep it compact. On the other hand, if it's a Neumann node, then I would like to add 1 to the DOFs and then update the corresponding value in the next column. So 2 times PD plus J is equal to DOFCs. So I'm basically looking at these values and updating these depending on the values here. So that's all I'm doing. All right. What's the problem here? Oh, it's lowercase j. All right. So that's it for these. Now, I also need to update the global DOF, because this is the part where it's going to put the nodes in order if you haven't done it here automatically. So let's look at here. I'm going to need the same 2 for loops because it's going to be the same movement. I'm going to go through the nodes and then problem dimension. And then if this number is less than 0, if this is negative, then what I'm going to do here is if ENL I 2 times PD plus J is less than 0, then ENL I 3 times PD plus J is equal to, which will be these values here. This value, and also it has to be the absolute value here. The absolute of this plus DOFs. So I think you should have seen this in class, but if you haven't, you can just ask me. So that's going to be it. Else, if this is larger than 0, I'm directly going to equate this to this term. So this is the whole thing. And at the end, I would like to convert DOCs to absolute DOCs. I don't want them to stay negative because we're going to use them later on. And we're going to return the exact same thing in here. So this completes the assign BC's function. Now, to import this function, let's just say import or from functions import all. So now the function is imported. Next, we're going to talk about the stiffness. So I would like to write another function named assemble stiffness. And this will give me the stiffness, assemble stiffness. And as the parameters, it will take ENL, EL, NL, the Young's modulus, and the area. So I'm going to take the whole global stiffness as a result of this function. Inside this function, I'm going to define, so let's say define assemble, or I can just copy this here. Yep. So let's just, all right. Now, let's start with defining number of elements, which will be np.size, the element list, the row count, and then let's also define nodes per element, which will be np.size el 1. So this is going to be 2 in this case, and this is going to be 3. I also would like to define the number of nodes in problem dimension as before. So I'm just going to copy these two here. Now let's look at the document here. So so the global stiffness matrix will be in the size of number of nodes times problem dimension times number of nodes times problem dimension. So in this case, it's going to be, let's say, number of nodes is 3, 2, so it's going to be 6 by 6. To get this, let's just generate it as zeros, number of nodes times PD, number of nodes times PD. All right. Now, for each element, I have to calculate their own stiffness, and then in the end, I'm going to combine their stiffnesses into this one giant matrix. So to calculate one element stiffness, as you know from the lectures, we use this equation. So E, A, and L are defined in the problem. All we need to do is define the cosines, sines, and calculate this for each element, and then we're gonna be fine. So let's just write a for loop for I in range from 0 to, for each element, number of elements. And then, okay, I'm going to define a mini node list, which will represent the node numbers corresponding to this selected element. So it will be, let's say, EL I from node per element. So it will take the first element from the element list, which will be 1 and 2. For example, if I were to be 0, and then it will take from the very start to the very end. So from 0 to 2, which will be 0 and 1. So it will take 1 and 2. Then I would like to define a lowercase k to represent the stiffness of one single element. And this is going to be from the function element stiffness, which takes the parameters, the mini node list we just defined, the extended node list, E and A. All right. So I'm going to switch to this function, definition element stiffness. Now we first need to define the x and y coordinates to get these cosines and sines. So let's say x1 is ENL, NL from, let's say, for the first node, it will be this and this. So NL0 will take the first node, which will be node number 1, and then I subtract 1 because in Python the indices start from 0 instead of 1. So I subtract 1, and then I want the first column of the ANL, which will give me the x coordinate, which is 0 in this case. So that's it. For the y coordinate, I would like to take the second column. So let's repeat this for the second element in this lowercase nl. This time I will change this to x2 and y2, and I'm going to change this to the second node in this mini node list, which will be 1 and 1, and yeah, that seems to be right. What's the problem here? Oh, in range, yeah. All right, so once we've done that, I also need to define the length of the, element. So to do this, I'm going to import math from Spider, import math, and then math dot square root of x1 minus x2 squared plus y1 minus y2 squared, which will give me the length of the element. After we take this, I also need to define the cosines and sines. So I will represent cosine with C, and then the cosine is going to be x2 minus x1 divided by L, and the sine is going to be y2 minus y1 divided by L. So once we've done that, we can now start calculating the stiffness. So what I'm going to do here is I'm going to do the exact same thing here. So the stiffness will be lowercase k is equal to E times A over L. E times A over L, and then times this numpy array, which will contain these terms. So let's start by the first row, cosine squared cosine times sine minus cosine squared, and then minus cosine times sine. So this is the first row. In the second row, we have c times s, s squared, minus c times s times s, and then minus s squared. All right. On the third row, minus c squared, and then minus c times s, then c squared and c times s, c squared, c times s, and then finally minus cs, s squared, minus cs, s squared, it has to has minus, and then cs, s squared, cs, s squared. All right, so let me check if we have any errors. This is going to be positive, this is going to be positive, this is negative, this is all right. So now we calculated the element stiffness. All we have to do is return this, return k. So once we've done that, we can go back to the original assemble stiffness function, which will calculate the global stiffness. So we have the stiffness of one element. Now we have to place it into this giant global stiffness matrix. So to do that, let's loop over for, let's say, r in range nodes per element. So I'm gonna go through every single element, and then I have to go through for p in range 0 to pd. So I'm gonna go through every single so nodes per element means I have 2 nodes. So for every single node, I'll go through x and y coordinates. So I have to go, so because of the form of the matrix, I have to go through these loops a second time. And let's name these Q and S. Now, first, I would like to identify the row, which will be row is equal to ENL, the mini node list we defined before, and this time it's going to be R -1 for index, and then P plus 3 times PD. To determine the column, this is actually very similar, but since I'm moving along the column, along the y-axis, I'm going to change this with Q and this with S. Finally, I have to find the value, which will be which will come from the stiffness, element stiffness we've calculated just a moment ago. So K R times PD plus Q, and then it's going to be the exact same thing, but I'm going to change this with P and S. Oh wait, so it's going to be RP and then QS. I'm sorry, my bad. So that's going to be it. So once we find a value, we have to place it on the correct slot on the matrix. So to do this, I'm gonna slice through this global stiffness matrix. We define the row, so it's gonna be integer row -1 for index, and then integer column -1 for index. And this is gonna be equal to whatever value we had there before, plus the value we just found. So as you've seen in the class, we keep adding element stiffnesses onto each other on different slots. So that's what we're basically doing here. So that's it. Once this loop is over, we can return K. And this is going to give us the stiffness, the global stiffness. So we got the global stiffness here. Now that we have the stiffness too, what I'm going to do here is to update these 4 slots in the extended node list. So as you might remember before, we defined these two matrices, and then now I'm going to use them. So ENL for every row, starting from 4 times PD to 5 times PD, which will give me, so 0, 1, 2, 3, 4, which will be equal to the displacement. So U, all the rows and columns. And then I'm going to do the exact same thing for the forces, but this time it's going to be the 5th and, the 6th and 7th columns. Oh, but because of the index, we have 5 and 6. So this is going to be, let's say, 8 and 9. From 8 to 10, which will be 8 and 9. And this will be from 10 to 12, which will be 10 and 11. And then I'm going to change this with this matrix that we defined before. So if you do this, now you can see that here, the forces are updated, the displacements are updated, DOFs and DOCs are updated, and we have the NL boundary conditions and all that. Now, all we have to do is calculate these question marks in the ENL. So these are going to change, and these 3 also are going to change. So let's go with that. To do this, I'm first going to flatten these, let's say, I'm first going to flatten these 2 matrices to use them later. You'll see why. And then fu.flatten. So this will basically turn this 2D matrix to 1, because that's how I need to use them. Now, I would like to find these unknown forces and unknown displacements. To do this, I'm going to define 2 different functions, assemble forces, and then assemble displacements. And the parameters for these two will be ENL and NL. All right, so let's go back to the functions and then add another function here, the definition assemble forces. Again, I'm going to define the number of nodes and the problem dimension just as before. So I'm just going to paste it. And then I'm going to define the DOF as 0. And then I'm also going to start this FP matrix as an empty list. I'm going to transform this into a matrix at the very end. This is just for the simplicity of the code. Now, again, I have to go through a loop for each node and each dimension, so x and y. For I in range 0 to number of nodes for each node, and then for each node, I have to go through each dimension. So it's going to be PD, problem dimension. So we're going to do the exact same thing we did before. So let's say if, let's see. Let's copy this from assign BCs and paste it here. Change this to 1. So if this is a fixed node, I have to add 1 to the DOF. And then I'm going to append this list with let's say, ENL, ith row, 5 times PD plus J. So 5 times PD plus J takes us to 0, 1, 2, 3, 4, 5 here. So I'm updating these two columns. So at the very end, I would like to stack all these FP values into one. So this is a trick that you that might be useful in your projects. You can just equate this list. You can turn this list into a NumPy array by doing this. So you're gonna stack np.vstack this whole list. And then I'm going to turn this into a 1D array. So -1 to 1. All right. So I'm going to do a very similar thing for the displacements. So I'm just going to copy this and then change this to displacements. So this time it's going to be DOC. And if this is -1, I would like to, oh, by the way, I have to add 1 here, plus here. And then I'm going to change this to UP. And by the way, this has to return FP as well. And this will return UP. So I'm going to change this to UP. This will be UP as well. This will be UP as well. And this time I'm editing these two columns, so this has to be 4. And we're pretty much done. All right. So let's go back to the code. Now, if we run this, as you can see, we have the forces, FP and UP. Where is it? Here. So that's it. Now, we need to multiply these using this expression. So you definitely have seen this in class. We have this matrix. So F is equal to K times U. So prescribed, unknown, unknown, and prescribed. I'm going to name the sections of the stiffness as this. And as you've seen in the class, the size of this top left matrix will be DOF times DOFs. And the sizes for the other sections will be like this. So let's start with KUU. All right. So let's say KUU will be equal to K. I'm going to slice through starting from 0 to DOFs. And also in the y-axis, I'm going to slice through DOFs because this is the size of the matrix. So that's it. Let's see this. So KU times P, KUP, slice through on the x-axis, it's going to be the same, DOFS. And then on the y-axis, I'm going to have starting from DOFs to DOFs plus DOCs. So I'm just adding DOF here to come here, and then add DOCs to come to the very end. So I'm just taking this whole thing. Now next up we have KPU. Let's just copy this, KPU. Now this time I have to go through the same thing as in KUP, but in the x-axis, so that's going to be it. So I'm just going to come here in the middle and then come to the very end. And then for the x-axis, I'm going to have this. And then finally, we're going to have KPP, which will be the very right bottom side of the matrix. So it's DOCs times DOCs, and this will be, this is going to be how we slice it. So this is how we're going to slice it. So once we've done that, we now have to take these, we now have to simplify this in 3 equations. So let's say, let's call this F is equal to FP we found before, minus NP dot matrix multiplication. To multiply two matrices, you have to use this function of numpy. So I'm going to multiply K UP by UP, and this will give me the forces. Then I'm also going to need the UU, which will be again NP dot matrix multiplication. This time I'm gonna take the inverse of KUU, because you know it's gonna be KUU divided by FP. Oh, I'm sorry, KUU divided by F. So if you take the inverse, you can just multiply it instead of dividing it. So this is going to be F. So we're multiplying the inverse of KUU by F. And then finally, we're going to have FU is equal to NP dot matrix multiplication. KPU by UP plus NP times matrix multiplication KPP times UP. I'm sorry, this one has to be UU. Yeah. Now, let's do this. Now, let's see the forces. Now you can see that the forces are updated. And also the displacement for each node is updated. Instead of being zeros, it's actual displacements. All we have to do now is to update this in the ENL2, because, you know, still these are not updated in the ENL, so I'm just going to plug these. Let's say ENL is equal to update nodes, which will take ENL, NL, and FU as the parameters. So let's just copy this and then go to the functions, add another function, and then this is going to return ENL. So just as before, I'm going to define these four. And then it's going to be the exact same loop we did here, but we're going to change just a small thing. So I'm just going to copy this and paste it here. So firstly, we have to change if this is 1, I'm going to add 1 to DOF. And then I'm going to change the forces. I'm going to change the displacements with DOFs minus 1 for index. So I'm just using the DOFs to place everything in the correct order. That's all I'm doing. It's the same algorithm we used in the boundary conditions. So that's it. The same thing's gonna happen, but this time this is gonna be 5 for forces, and it's gonna be DOCs. And this is gonna change as FU slice DOCs minus 1 for index. And yeah, that's pretty much it. So if you go back to here and run this, now you can see that every displacement and force is replaced by the updated versions. So from here, we can proceed to the post process. But we're going to talk about it in the next hands-on session video. You can ask me your questions via email, or we can arrange a Zoom meeting if you have any. I know it's a little bit complicated, but if you follow the process from this document, it's pretty clear, I think. But you can still ask me your questions, as I said before. Anyways, I'll see you guys in the next video. Take care.